Okay, so this is chapter 23, picking up at slide 100. So we've talked about the differences between respiration and ventilation, and now we're down at the actual exchanges, okay? So gas exchanges, we're going to be exchanging oxygen and CO2, and it has to occur between the blood and the alveolar air across the blood-air barrier. And the speed and direction of the exchange depends on the partial pressure of the gases involved and the diffusion of molecules going from a gas to a liquid or a liquid to a gas. So the diffusion of gases occurs in response to their concentration gradients, just like all other diffusion gradients. And the rate that they diffuse depends on the different physical principles or gas laws, for example, Boyle's law. Dalton's law says that each gas in the air contributes to the total pressure in proportion to how much of that particular gas is in the air. For example, let's just make up a number. Let's say that oxygen makes up, 75% of the air that's around us. Now, it's nowhere near that, but let's just say it did. Then it would also contribute 75% of the pressure. Okay, so here's the actual numbers. The pressure contributed by a single gas in a mixture. In our normal air, the total pressure is 760 millimeters of mercury. Nitrogen is actually the most abundant. That might surprise you. It is 78.6% of all the gas in the air. And so if you take 78.6% of 760, that means that out of that 760, 597 millimeters of that pressure is coming from nitrogen. Oxygen is second. It's almost 21%. Water vapor is 0.5%. And look at this. Carbon dioxide in the atmosphere is so low. It's 0.04%. So only 0.3 millimeters of mercury. So you have a decent amount of oxygen in the air around you in the atmosphere, about 21%, and very little CO2. Now, to get things to diffuse between a gas and a liquid, we have to take into consideration Henry's law. That says at a given temperature, the amount of gas in the solution is proportional to the partial pressure of the gas. And when the gas under pressure contacts a liquid, that pressure forces the gas into the liquid, into a solution. And so if we just let it go into and out of the gas based on diffusion, at equilibrium, the gas molecules diffuse out of the liquid as quickly as they enter it. So the number of gas molecules in the solution will be constant. Okay? So here's the example. Here's a soda can. This is something we all have some experience with. So when they can a can of soda, they infuse it with CO2 gas, right? Carbon dioxide. And it's saying that that little bit of space at the top of the can where there's air, the gas molecules are going into the soda and into that airspace at an equal rate all the time. So as long as we don't change the volume of the container, which would change the pressure, then they're going to be entering and exiting the solution evenly. If I open the can, now those same CO2 molecules, when they come out of the solution, are going to enter the air around it. Because guess what? It has a much lower concentration of CO2. And so over time, we will get less and less molecules being forced back into solution because they now have all this expanded space to be in. That's why your soda goes flat if you leave it open. So in the air-blood exchange, we have air, the gas is in atmosphere, and then it has to go into blood, which of course is a fluid. Now, also we have to worry about how soluble is each gas in fluid. CO2 is highly soluble, that's like dissolvable. O2 is less soluble, and nitrogen has extremely limited solubility. So, if we were to look at the partial pressures of these three gases in the plasma of a pulmonary vein. So what's a pulmonary vein? We've just left the lung and we're going on our way back to the heart, okay? The giant P stands for partial pressure. The partial pressure of CO2 is 40 millimeters of mercury. Now remember, we just dropped off CO2. So this is the lowest pressure we would see of CO2 in the blood. For oxygen, we are at 100 millimeters of mercury. This is the highest oxygen level we will see in the blood. And then for nitrogen, it's 573 millimeters of mercury. So when the when the gases diffuse from the blood-air barrier, the direction and rate are determined by their different partial pressures and their different solubilities. So reasons for how fast gas exchanges happen. They're going to be the differences in the partial pressures. So when you have more of a gas in the air than you do in the blood, that gas is going to be driven by the pressure of the air into the blood. If you have more of that gas in the blood than in the air, it's going to be coming out of the blood and into the air. We also have made the distance between the blood and the air sac as small as possible. Both oxygen and CO2 are lipid soluble, so they can go right through the cell membranes. We have a lot of total surface area in the alveoli, and we're going to be coordinating how fast the blood is going past the alveoli with our breathing rate. Okay, so this is why our respiratory system does such an awesome job at assisting us with this exchange. So, external respiration is what's happening at the lungs. So blood that has come in from the right ventricle of the heart, it's coming in the pulmonary artery, has a low partial pressure of oxygen, but we have just picked up CO2 from all those capillary beds. So we have a high partial pressure of CO2. Because these oxygen is low in the blood, this causes oxygen to enter the blood. Because CO2 is high in the blood, that causes CO2 to leave the blood. So at the lungs, we pick up oxygen and we push out carbon dioxide. This happens really quickly, and they go across the blood and alveolar air to reach equilibrium. Then when we get out to the capillary beds, okay, we take that oxygenated blood and low CO2 containing blood all the way down to the cells. Well, the cells have been generating CO2. And so the CO2 will leave from the interstitial fluid and go into the blood. And the oxygen, which is high in the blood, has been used up by the cells. So it will go from the blood into the interstitial fluid and eventually into the cells. So oxygenated blood mixes with deoxygenated blood from conducting passageways. This lowers the partial pressure of oxygen in blood to about 95. So we lose about 5 millimeters of mercury in this mixing. And then the interstitial fluid, we have the partial pressure of oxygen is 40 millimeters of mercury, and the partial pressure of CO2 is 45. So this drives CO2 into the blood from the interstitial fluid and oxygen out of the blood into the interstitial fluid. So here's a little diagram up here to show that. So here's my capillary, here's the alveolus. This is external respiration. So this is what's happening at the lung. So the partial pressure of oxygen in the atmosphere is 100, and the partial pressure of oxygen in the blood before this is only 40. So you have 60 more millimeters of mercury of pressure driving oxygen into the blood. So this will raise this up to equilibrium. So we now have 100 millimeters of mercury in the blood of oxygen. Okay. For the CO2 was 45 in the capillary, and it was only 40 in the air. So we're going to push and go to equilibrium, and so it only stays at about 40. So CO2 concentration really only changes by about 5 millimeters of mercury. Now, down at the capillary bed, we had our 95 of oxygen. Remember, we lose a little bit of oxygen by mixing it with deoxygenated blood. And then we have our 40 of CO2. We come by this interstitial fluid, which has collected the CO2 from all of these different cells. And oxygen is only 40. So we go from 95, that's 55 more millimeters of mercury. So oxygen gets pushed in here, right? And then this drops to 40 because it equalizes. For CO2, we're at 45 here and 40 here. So we have CO2 enter the blood to reach equilibrium. Blood plasma cannot by itself transport enough oxygen or CO2 to meet all the demands of the cells. So that's where red blood cells come into play. Their job is to bind up more oxygen so we have more efficient transport, and they can also bind CO2. So they transport oxygen to and CO2 from peripheral tissues, and the red blood cells remove oxygen and CO2 from plasma, allowing gases to continue to diffuse into the blood. So oxygen binds to the iron that is in the center of hemoglobin, and it's a reversible reaction. When it is bound to oxygen, we call it oxyhemoglobin. When it releases the oxygen, we call it deoxyhemoglobin. Each red blood cell has about 280 million hemoglobin molecules, and each of those can bind 4 oxygen molecules. Now, a molecule of oxygen is O2. So imagine it's actually 8 individual oxygens for each of those 280 million hemoglobins. At some point, all of the hemoglobins are going to be covered with oxygens, and that's called hemoglobin saturation. And things that will affect the hemoglobin saturation are the partial pressure of oxygen in the blood's pH, and the blood's temperature, and the metabolic activity within the red blood cells. So there's this curve that shows how well the hemoglobin binds to the oxygen at different conditions, okay? The higher the partial pressure of oxygen, the more oxygen gets bound to hemoglobin. It's a curve rather than a straight line because hemoglobin has to change shape every time a molecule of oxygen binds, and every new bound oxygen makes the next bound oxygen come more easily. Okay, so if you're looking at the curve, it's standardized for a pH of 7.4 and our regular body temperature. And we just said pH and body temperature affect the binding. If the pH drops, so the blood becomes more acidic, or if the temperature starts to rise, then the hemoglobin is more apt to let go of the oxygen. If the pH goes up, so we can become more alkaline, or the temperature drops, the hemoglobin tends to hold on to the oxygen more tightly. So if I'm letting go of oxygen, the entire curve shifts to the right. If I'm hanging on to oxygen, the entire curve shifts to the left. And here is that curve. So that's showing you at the different pressures of oxygen, how much of the hemoglobin is saturated. Remember, we start out here at 100 millimeters of mercury at the lungs. And so 97.5% of those red blood cells are bound to hemoglobin. Oxygen are bound to this hemoglobin on the red blood cells. Okay? And as we get less millimeters of mercury, we're going to lose the ability to hang on to the oxygen. So hemoglobin and pH. The Bohr effect is that effect by pH. It's the effect of pH on the saturation of hemoglobin caused by carbon dioxide. So carbon dioxide being high diffuses into the red blood cells, and there is an enzyme there called carbonic anhydrase that catalyzes a reaction with water and causes these two products, carbonic acid, and then carbonic acid, you can tell is an acid, will come apart and release hydrogen ions and bicarbonate ions. This is called the carbonic acid bicarbonate buffer system. This is what usually keeps the pH of your blood rather constant. Okay? So this is caused by high amounts of CO2 in the blood. The hydrogen ions will leave the red blood cells and they will lower the pH of the blood. What happens if we have lower pH of the blood, if it becomes acidic? Well, then we hang on to the oxygen more tightly. So here's where we were standardized. Our curve was here, 7.4. If we lower the pH of the blood to 7.2, we do not release the oxygen as easily. So our saturation curve is less. If we raise the pH of the blood and make it go alkaline, we release it more readily. Same thing with temperature. Temperature increases, we let go of oxygen more easily. When temperature decreases, we hold on to oxygen more tightly. Temperature effects are significant only in active tissues that are making a large amount of heat, like your skeletal muscles. Okay, so here's our normal temperature is 38 degrees Celsius. At 43 degrees, we shift the curve to the right. At 10 degrees, we shift the curve far to the left. Red blood cells, because they lack all sorts of organelles, they're basically just a bag of hemoglobin, they don't have mitochondria to generate ATP. So they can only make ATP by a process called glycolysis. Now, during glycolysis, we form something called lactate or lactic acid and another thing called 2,3-bisphosphoglycerate, BPG. BPG directly affects oxygen binding and release. So the more BPG we have, the more oxygen gets released. And as BPG levels rise, they will rise in response to increase in pH, becoming more alkaline, or certain hormones. If BPG levels are too low, the hemoglobin will not release the oxygen at all. So fetal hemoglobin is slightly different from adult hemoglobin in the fact that it binds oxygen more tightly and more easily. So when mom is pregnant and she has oxygen on her hemoglobin and it comes to the placenta, the baby's blood in the placenta takes the bulk of the oxygen away from mom to get it to baby. So mom often feels tired and out of breath and lacking energy because literally her baby's taking all her oxygen. Okay, so you can see the curve. All right, what about other compounds? What about carbon monoxide? Carbon monoxide, notice it's carbon with only one oxygen. Guess what? It binds more strongly to hemoglobin than oxygen does, and it does not like to be released. And so if you are in an environment where you're breathing in carbon monoxide, you will replace all your spots on your hemoglobins with this molecule, and there's no room for oxygen. And so what you can have is carbon monoxide poisoning, where you actually starve your entire body and especially your brain of oxygen, leading to death. The only way to drive off the carbon monoxide after it is bound to hemoglobin is to put people in a chamber with pressurized oxygen that forces the carbon monoxide off of the hemoglobins. Okay. What about carbon dioxide transport? We just said the cells are producing CO2 during their aerobic respiration, and it's bad, it's toxic. And so we need to get it away from the cells and take it through the bloodstream. And it can be carried in the bloodstream 3 ways, as opposed to oxygen, which really only has 2 ways. It can be converted to carbonic acid. It can bind to hemoglobin and create carbaminohemoglobin. Or it can be dissolved in the liquid part of the blood, the plasma. 70% of it is actually transported as bicarbonate. And we just saw how that happens. CO2 diffuses into the red blood cells. It goes to carbonic acid. Carbonic acid falls apart and becomes hydrogen ions and bicarbonate. The hydrogen ions bind to the hemoglobin, and bicarbonates move into the plasma, and it moves them in exchange for chloride ions. So this is called the chloride shift. Only 23% of carbon dioxide is bound to the hemoglobins. And then the last 7%, not very much, is in as a dissolved gas in the plasma. All right, so there's a lovely graphic for you. So, again, we're back in the lungs, okay? We have plasma and red blood cell. Oxygen comes in from the alveolar airspace. Some of it is in the plasma, but most of it ends up bound to hemoglobin. We get out to the capillaries. The hemoglobin releases the oxygen very readily. Oxygen from the plasma also goes into the interstitial fluid to the cells. For the CO2 at the lungs, we have carried it in the plasma, we have carried it bound to hemoglobin, and we have carried it as carbonic acid. So all of these CO2s, when we get to the lungs, will go back into the alveolar airspace and be exhaled. And then at the cells, we draw in the CO2 and put it in the plasma. We bind it to hemoglobin, and we carry it as carbonic acid and bicarbonate. And we cause the chloride shift here, and we put out the bicarbonate ions into the plasma. Okay, so this might surprise you, but your body is more sensitive to the concentration of carbon dioxide than it is to the amount of oxygen. It is the carbon dioxide levels that send off the alarm bells. So for local regulation of respiration, if you have CO2 partial pressures that are going up, that presence of this gas will cause you to relax your smooth muscle in your arterioles and capillaries to make the blood flow faster. it's accumulating too quickly. We need to get it out of the blood through respiration. So we speed up the blood getting to the lungs. Your ventilation to perfusion ratio, or VQ ratio, coordinates with your lung perfusion, how the blood is going through the alveoli areas, to your breathing. And your PCO2 levels control your bronchoconstriction and bronchodilation to match those airflow to blood flow. Now, this is ultimately controlled by the respiratory center of the brain. Now, that was local. This is like systemic control. When your body needs more oxygen, it will tell your breathing apparatus to increase breathing rate. And it has some parts that are voluntary and some that are involuntary. The voluntary part is in the respiratory center of the pons and medulla. And those are going to be to your voluntary muscles that control your respiratory muscles, like your diaphragm. The respiratory centers are 3 different clusters of nuclei in the reticular formation, and they are going to control how often and how deeply you breathe. So these are the respiratory rhythmicity centers. And there is a dorsal respiratory group and a ventral respiratory group. So one's going to be on the back, one's going to be on the front, right? Of the medulla. The dorsal respiratory group is for inspiration, inhaling, and it works in both quiet and forced breathing. Now, quiet breathing is active inhale, passive exhale. For quiet breathing, those particular neurons stimulate the muscles for inspiration, and then they become inactive while you exhale passively. There's quiet breathing. The ventral respiratory group is going to have both inspiratory and expiratory centers, and it only activates during forced breathing. Now, forced breathing is going to be caused by an increased activity in the dorsal respiratory group, and it's going to bring in our accessory inspiratory muscles. So normally we just inspire with our diaphragm and our external intercostals. This will then cause us to recruit other muscles for inspiration. And it also causes active exhalation. So inhalation, muscles of inhalation contract, and we relax the opposing muscles. We activate both the DRG and the VRG, and the expiratory center is active. We actively exhale, and then we go back to the inspiration. And here's just a diagram to show where those centers are. The respiratory centers are monitoring sensory information from the chemoreceptors that are looking at the levels of CO2 and the levels of oxygen and the pH of blood, or the pH of the cerebrospinal fluid. So for pressures, we're going to use baroreceptors. We're also going to use stretch receptors that are looking at lung volume. We're going to have any kind of irritating physical or chemical stimuli in the nasal cavity, larynx, or bronchial tree can set off some of these reflexes we're going to see. And we can even have things like pain, fever, or any abnormal visceral sensation. So that means any organ feeling uncomfortable, painful, any malfunctioning could actually change your breathing rate. If the chemoreceptors are stimulated, it makes you breathe deeper and faster. And it's subject to adaptation, which means the more that particular chemoreceptor is activated, the less it will affect your breathing rate. Hypercapnia is when you have too much partial pressure of CO2. So you have CO2 gas building up in your bloodstream, caused by you not breathing fast enough. Hypoventilation causes hypercapnia. So what happens is when you have a high amount of CO2 in your blood, it stimulates you to breathe faster and deeper. Okay. So if someone, and we'll get to that. Hypocapnia is too little CO2 in your blood, and it's caused by breathing too quickly and too shallowly, and so you have hyperventilation. So these chemoreceptors shut down and your respiratory rate falls. Now, if you are hyperventilating, since the problem is low partial pressure of CO2 in your blood, a very good solution is rebreathing. That means you breathe your CO2 out into a bag and then re-inhale it. That will drive up the partial pressure of CO2 and it will solve hypocapnia. And here is a nice graphic for that. The baroreceptor reflexes are in those same spots we discussed before, the carotid and aortic baroreceptors, looking at your blood pressure. If your blood pressure falls, your respiratory rate increases. If your blood pressure increases, your respiratory rate decreases. Apnea is when you're not breathing at all. A long time of suspended respiration. Usually, if you stop breathing, you will follow that with a big, very forceful expulsion of air to remove a stimulus, and this is what happens in sneezing and coughing. You can also have a laryngeal spasm that closes your airway to keep things from going deeper down into your trachea. And things that change in babies before birth, their pulmonary vessels are collapsed, their lungs have no air. During delivery, they lose the connection to the placenta, so that's where their oxygen was. That causes their blood partial pressure of oxygen to fall and CO2 to rise. And so the newborn at first has to overcome surface tension to inflate the bronchial tree. This causes a huge drop in pressure and pulls blood into the pulmonary circuit. This drop also closes the foramen ovale and ductus arteriosus, and it now establishes the normal blood pattern through both the pulmonary and systemic circuits. And every other breath will fully inflate the alveoli. So the goal of your respiratory activity is to make sure that you have proper O2 and CO2 levels in peripheral tissues, and you have to then have communication between your respiratory and cardiovascular systems. That controls how fast the blood is going past the alveoli, how deeply and often you are breathing, and we have to have feedback, of course, to make sure that everything is proceeding normally. And here's our normal end of chapter, showing how these two systems are related to each other, but also how they're related to all of these other organ systems that we've already covered. All right, guys, so that's the end of 23. 24 is over 200 slides, so buckle in. We're going to be probably at least 4 or 5 videos for that chapter, and that will be posted soon.